Okay, this is Vector Calculus, Lecture 17. The second midterm exam is in about 2.5 weeks. It's going to be Wednesday, April 18th, on campus at 11 o'clock. And we'll say more about the exam as it gets closer, of course. What we've been talking about most recently are tangent planes and linear approximations to functions. And the new topic that we'll discuss today is maximum minimum problems. Are there any questions about any of the homework that's been assigned? Okay, so let's just take a kind of review look. Remember, in Calc 1, you have a curve, y equal f of x. And at any point on the curve, there's a derivative. So at the point A, this is the point A comma f of A. And we can draw the tangent line to the curve at the point, which is given by y equals the slope of the line is the derivative of f prime of A, x minus A plus f of A. And this is a linear approximation to the curve f of x near the point x equal A. In Calc 3, which is this course, vector calculus, we might have a function of two variables, z equals f of x, y. So the graph of this function is a surface. And at a point AB in the plane, in the domain of the function, you have the point AB comma f of AB, which is a point lying on the surface. And analogous to the tangent line to a curve, you have the tangent plane. And this is the plane through the point AB, f of AB, with normal vector equal to the gradient of f at AB.
Hello, Professor.
Yes.
Hi, excuse me for the interruption. I see you put the next exam April 18th. That's a Thursday. I have
Oh,
another
sorry.
class
No,
at
no, no,
a,
no. That's a mistake then. It's a Wednesday.
oh, it's the 17th, okay?
Let me just double check. April. Yes. Sorry. April 17th.
Okay, awesome. All right, thank you.
Right. I mean, it has to be class time, so
Okay, all right.
it
Thank
wouldn't
you.
be any unusual time. So this is the tangent plane at this point on the surface is a plane through the point, and the plane is determined by a normal vector at a point. And the normal vector is the gradient. So So it's the plane through the point AB, f of AB, with normal vector equal to the gradient, with the partial derivative of x at AB, partial derivative at y at AB. Those are the coordinates of the gradient. So, for example, actually, let me do this more like the way it's done in the text. So it starts with a function of three variables. So this is alternative approach, if you like. If you have a function f of x, y, z, a function of three variables, and we look at the level surface, f of x, y, z equal to 0. And when we start with a function of three variables, f of x, y, we're going to let capital F of x, y, z be equal to f of x, y minus z. But for a function of three variables, if you take the level surface f of x, y, z equals 0, the tangent plane at a point A, B, C on the surface, that means f at A, B, C is equal to 0, is the plane through the point A, B, C with normal vector equal to the gradient of f is the normal vector at ABC. So this is the vector with coordinates, partial of f with respect to x at ABC, partial of f with respect to y at ABC, partial of f with respect to z at ABC. So the equation of the plane so the point x, y, z lies in the plane if the vector from x, y, z to ABC is orthogonal or perpendicular to the gradient of f at ABC. And the vector from x, y, z to ABC is the vector with coordinates x minus a, y minus b, z minus c. So that vector is perpendicular to the gradient. That means the dot product is 0. And the dot product of these two vectors is, it should be a capital F. Capital F sub x at ABC, that's a number, times x minus a, partial of f with respect to y at ABC, y minus b, plus partial of f with respect to z at ABC, times z minus z equals 0. So this long equation is the equation of the tangent plane. And let me work out an example. So let me turn to the exercises and maybe and the problems at the end of this section, number 14. Suppose you have the function f of x, y, z equals x squared plus y cubed plus z to the fourth, or And we're looking at the level curve, or the level surface, x squared plus y cubed plus z to the fourth equal 2. So we should actually say let capital F of x, y, z be x squared plus y cubed plus z to the fourth minus 2. And we're looking at when this is equal to 0. That's the same as x squared plus y cubed plus z fourth equal 2. We want to set this up the way it's done in the text. Then you have this function of three variables, x squared plus y cubed plus z to the fourth minus 2 equals 0. And if we compute f of 1, 0, 1, that's 1 squared plus 0 squared plus 0 cubed plus 1 to the fourth minus 2 is 1 plus 1 minus 2 is 0. So 1, 0, 1 lies on the surface. What is the gradient of f? The partial with respect to x is 2x. The partial derivative with respect to y is 3y squared. The partial derivative with respect to z is 4z cubed. So the gradient of f at this point on the surface, 1, 0, 1, is 2, 0, 4. So the tangent plane will be 2 times x minus 1 plus 0 times x times y minus 0 plus 4 times z minus 1 equals 0. So this is 2x minus 2 plus 4z minus 4 equals 0, or 2x plus 4z equals 6, or x plus 2z equals 3. So that's the tangent plane. Now, if we have the function f of x, y, and we look at the graph of this function, this surface, so, and let f, capital F of x, y, z equal f of x, y minus z. And suppose we let c be equal to f of ab, then f of abc is f of ab minus c. That's f of ab minus f of ab. That's equal to 0. So the level surface, f of xy, capital F of xyz equals 0, is just the graph of this function. So for this function, what is the gradient of f? It's the partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z is minus 1. So the equation of the tangent plane is the partial of f with respect to x at ab times x minus a plus the partial derivative of y of f with respect to y at ab times y minus b plus the partial derivative of f with respect to z at ab, which is minus 1, so it's just minus y z minus f of ab. So this is, if you rewrite this equation, the plane is z equals partial of f with respect to x, partial of f with respect to x at ab times x minus a plus the partial of f with respect to y at AB times y minus b plus f of AB. And if you compare that to the tangent line of a curve for a function of one variable, see here, the plane is z equals partial of f with respect to x times x minus a, partial of f with respect to y times y minus b, plus the value of the function at AB. For one variable, it was exactly the same thing. But the partial derivative is just derivative. The derivative at a times x minus a plus the value of the function at a. Here it's this, which is like the derivative of f. It's the gradient of f at AB plus the value of the function at AB. So this tangent plane equation is exactly the two-dimensional analog of the one-dimensional tangent line from calculus 1. Okay. And it's useful sometimes to think of that. So let me just write this down. Again, the tangent plane for a function z equal f of x, y, at the point AB, it's partial of f with respect to x at AB times x minus a, partial of f with respect to y at AB, y minus b, plus the value of the function f of AB equals z. So that's the equation of the tangent plane. And let me do another, let me just do an example of this. This is number 17. We have the function z equals 4 minus 2x squared minus y squared. And if you check, if you take 4 minus 2 times 2 squared minus 8 squared, what is that? So this is like I'm looking at the function z equal f of x, y, which is 4 minus 2x squared minus y squared. So f of 2 comma 2 is 4 minus 2 times 2 squared, which is 4, minus y squared. Minus 4. That's 4 minus 8 minus 4 is minus 8. So the point 2, 2 minus 8 lies on the surface. Because when x is 2 and y is 2, f of x, y is minus 8. For this function, the gradient of f is minus 4x minus 2y. The gradient of f at 2, 2 is minus 4 times 2 minus 2 times 2. This is minus 8 minus 4. So these are the partial derivatives of f with respect to x at AB. So the tangent plane is z equals partial derivative of f minus 8 times x minus 2 plus the partial of f with respect to y minus 4 times y minus 2. So this is minus 8x minus 4y plus 16 plus 8 plus 24. plus 16 let me just check my arithmetic here. So z is 4 minus 2x squared minus y squared. Partial of f with respect to x is minus 4x. And when x is 2, that's minus 8. Partial derivative of z with respect to y is minus 2y when y is, oh, I forgot, add f of ab. So it's minus 8 times x minus 2, minus 4 times y minus 2. And for this function, f at 2, 2 is minus 8, minus 8. So you get minus 8x minus 4y plus 16. So that's the equation of the tangent plane. And if I write this as L of xy equals minus 8x minus 4y plus 16, then for xy near the point 2, 2, f of xy is approximately equal to L of xy. That is, we have our surface, and on the surface, we have the tangent plane, and for points, so this is like the point AB, for points in which in this case is 2, 2. So for points close to this point 2, 2, the value of the function is approximated well by this plane. So what that says is that f of xy, which is 4 minus 2x squared minus y squared, is approximately minus 8x minus 4y plus 16 for the point xy near the point 2, 2. This is what it means to say that the function is approximated by the tangent plane close to the point. And let me do an example of that. I like to pick examples from the back, from the text, because it makes it easier for you to study everything by yourself, and keep in mind that all the odd numbered problems have answers in the back of the book. So in section 15.6, problem number, let's say 35, we have the function f of xy equal to minus x squared plus 2y squared. And we take the point P with coordinates 3, minus 1. So the gradient of f at xy is minus 2x 4y. The gradient of f at 3 minus 1, when x is 3, you get minus 6. When y is 1, you get minus 4. And of course, the value of the function at 3 minus 1 is minus 3 squared plus 2 times minus 1 squared is minus 9 plus 8 is minus 7. So the tangent plane at the point 3 minus 1 is given by z equal partial of f with respect to x at 3 minus 1, x minus 3, partial of f with respect to y at 3 minus 1 times y minus minus 1 plus the value of the function at 3 minus 1. So the partial derivative with respect to x is minus 6 times x minus 3. Partial of f with respect to y is minus 4. Y minus minus 1 is y plus 1. And the value of the function is minus 9 plus 2 is minus 7. Minus 7. So z is minus 6x minus 4y plus 18 minus 4 minus 7. So z is minus 6x minus 4y. 18 minus 11 is 7. So that is the tangent plane. So f of xy minus x squared plus 2y squared is approximately, let's call it L of xy, which is minus 6x minus 4y plus 7. And the approximation part of the problem is to estimate f at the point 3.1 minus 1.04. So this is approximately L evaluated at 3.1 minus 1.04. So 6 times 3.1, that's minus 18.6, minus 4 times 1.04 is plus 4.16 plus 7. So let's see if I can do this arithmetic. I have 11.16 and 18.60, and when I subtract, I get 4, 4, 7. So minus 7.42 plus 7 is minus 0.42. So something doesn't look quite right here. Minus 6x minus 4y plus 7. So minus 6 times 3.1 is minus 18.6. 4 times 1.04 is plus 4.16 plus 7. So, oh, I'm sorry, this is 7. 18.60 minus 18.60 plus 11.7. So that's minus 7.44. So this is my approximation to the value of the function at 3.1. And it's easier to compute this than to compute exactly what is f of 3.1 minus 1.04. It's going to be minus 3.1 squared plus 2 times 1.04 squared. What does that equal to? Well, you can do it by hand, and it takes a while. You can do it by your calculator, which is quick, but I don't have a calculator, but let me just do it on my computer. So this is minus 3.1 squared. Oops, what's going on here? Just 1 second. Minus 3.1 squared plus 2 times 1.04 squared and this is exactly minus 7.4468. And my approximation was minus 7.4400. So that's not bad. That is a respectable approximation. Any questions about this? Okay. Now there's one more topic in this chapter I'm going to cover. And again, it's very similar to what you did in Calculus 1. Remember in Calc 1, you might have a function, y equals f of x, and you have a relative maximum or a relative minimum at a critical point. All right, so A is a critical point if the derivative at A is 0. Now, this is a local maximum, this is a local maximum, this is a local minimum. At those points, the derivative of the function is 0, but how do you tell where you have a maximum or a minimum when you're at a critical point? So for that, I hope you remember, there was the second derivative test. Second derivative test. If f prime of A is 0, that means you're at a critical point, and the second derivative is negative, this means you have a relative maximum. If the first derivative is 0 and the second derivative is positive, you have a relative minimum. If the first derivative is 0 and the second derivative is also 0, you have no information from the test. So this doesn't give you a complete criterion for finding maxima and minima, but it often gives you, it often does give you the information. When does it fail? Well, you could have a function like f of x equal x cubed. So the graph of that function looks like this. And at x equals 0, the derivative of x cubed is 3x squared. So the derivative at 0 is 3 times 0 squared is 0. So x equals 0 is a critical point. But when you look at the second derivative is 6x. Second derivative at 0 is 0. And in fact, if you look at this point, you see you don't have a maximum or a minimum. You have what in this case is called an inflection point. So this is an indication that the first derivative being 0, that is, being a critical point, is a necessary condition to have a relative maximum or minimum. And to distinguish the two, you can look at the second derivative. But that only tells you, that only distinguishes between maxima and minima where the second derivative is non-zero. Right? So that is what you learned in first semester calculus. And we want to do something analogous for surfaces. We want to study maxima and minima for surfaces. So for example, if you have a kind of paraboloid, this point here at the bottom will be a relative minimum. Or sometimes these are called local minimums, local maximum. And how do you find such a point? That's the question. So we have something very similar to the situation for functions of one variable that carries over to functions of 2 or 3 variables. So suppose we have a surface z equal f of xy. So what is the formal definition of a local minimum or a local maximum? So we say that AB is a local maximum of the function z equal f of xy if f of AB is less than or equal to f of xy for all xy in some open disk with center at AB. In other words, in the xy plane, z is a function of x and y. The point AB lies in the domain of the function, and there's some open disk around AB, some little circle. And at every point in this open disk, and the radius can be as small as you like, but at every point in this open disk, the value at AB is less than or equal to the value of xy. And similarly, sorry, what I just defined is the local minimum. Should get that right. And AB is a local maximum of the function z equal f of xy if f of AB is greater than or equal to f of xy for all xy in some open disk with center at AB. So if you think of what the picture of this might look like, let's say this point AB is a local maximum, which means if you take any curve through that point, on that curve, AB will be, f of AB will be bigger than it is at any point nearby on the curve. So if you take the curve parallel to the x-axis, you would get that. So at a local maximum, partial of f with respect to AB is going to be 0 on that curve. On that curve, the curve's going to look like that. And similarly, at a local minimum, the partial of f with respect to AB will be 0 because the curve at that point will look something like that. And similarly, if you take a curve parallel to the y-axis, so both partial derivatives will be 0 at a local max or a minimum. And such a point is called a critical point. The point AB is a critical point of the function z equal f of xy if the partial of f with respect to x at AB and the partial of f with respect to y at AB are both equal to 0, which is the same, of course, as saying that the gradient of f at AB is 0. We also say there's a critical point if one or the other or both of the partial derivatives doesn't exist. So if you have the function f of x, y equals xy, x minus 2, y plus 3, and the problem is, so this is an example, find the critical points. So the partial of f with respect to x is what? Well, by the product rule, it's the derivative of xy, which is y, times x minus 2, y plus 3, plus xy times the derivative of x minus 2, which is 1, times y plus 3. So this is equal to, if I want to simplify it a little bit, if I factor out the y plus 3, I get xy minus 2 plus xy. That's 2xy minus 2. And the partial of f with respect to y is going to be x times x minus 2, y plus 3, plus xy times x minus 2 times 1. If I factor out the x minus 2, I get xy plus 3x minus 2xy. So that's minus xy plus 3, or minus xy minus 3. And I want to find the points where these are both equal to 0. So y, x minus 2, y plus 3, plus xy, y plus 3. I could have factored out y times y plus 3. And then I'm left with x minus 2 plus x, which is 2x minus 2. So I could factor out a 2. 2y, y plus 3, x minus 2 equals 0. And in the partial derivative of f with respect to y, I could have factored out x times x minus 2. And that leaves me with y plus 3 plus y, which is 2y. So factor out x times x minus 2. Y plus 3 plus y is 2y plus 3. Always good to get this right. So if I have the function f of xy equal xy, x minus 2, y plus 3, to find the critical points, these are the points xy, where the partial of f with respect to x, which is 2y, x minus 1, y plus 3 is 0. And the partial of f with respect to y, which is x, x minus 2, 2y plus 3 equals 0, where both of these equations are satisfied. So for this equation, this is equal to 0 when either y equals 0 or y equals minus 3 or x equal 1. And this is 0 when either x equals 0 or x equal 2 or y equals 2y plus 3 equals 0, means y is minus 3/2. So where are the critical points? If y is equal to 0, then x, then this is 0. This has to be 0, so x equals 0 or 2. If y equals minus 3, then x equals 0 or 2. And if x equals 1, then y equals minus 3/2. So you get 5 critical points. Zero, let's see, y equals 0. So you have 0, 0, 2, 0, 0 minus 3, 2 minus 3, and 1 minus 3/2. So those are the critical points of this function. Right. Any questions about this? I mean, it's really important to do a lot of exercises, more than just than the ones that I assigned. To learn how to do these kinds of calculations. Now, you remember for a function of one variable, where you have a critical point, which means the derivative is 0, you could have a local maximum or a local minimum, but you might have an inflection point. It's a point which looks like this, which is neither a local minimum nor a local maximum. Around this point, no matter how close you want to get, you will always find points which are both larger and smaller than the value of the function there. And something analogous happens for functions of 2 variables. And instead of calling them inflection points, they're called saddle points. So a saddle point of the function z equal f of xy is a critical point, AB. Critical point means both partial derivatives of the function are 0. It's a critical point such that in every open disk centered AB, there are points xy such that f of xy is bigger than f of AB, and also points xy with f of xy less than AB, less than f of AB. So this is just like the picture we saw for an inflection point for a function of one variable. Close to this inflection point, there are points where the value of the function is greater than its value here, and there are points where the value of the function is less. That is, where the curve is above this point and the curve is below this point, arbitrarily close to this point itself. So the analog of an inflection point for a function of one variable is a saddle point for a function of 2 variables. And just as we had a second derivative test for functions of one variable, there's something completely analogous. There is a second derivative test for functions of 2 variables, which allow you to tell whether a critical point is a local maximum or a local minimum or a saddle point, but sometimes it just also gives no information. So we assume we have this function which has continuous second partial derivatives. Right? Not every function is differentiable. Not every function that has a derivative has a second derivative, and not all derivatives are continuous, but most of the functions, and really all the functions we look at in vector calculus, have continuous partial derivatives of all orders. So the second derivative test for a function z equal f of x, y at the critical point AB. So the question is, what kind of second derivative do you look at? Now, for a function of one variable, there's only one derivative and one second derivative. But for a function of two variables, you can take the partial derivative of f with respect to x, and then take the second partial with respect to x at the point AB. Or you could take the partial derivative of f first with respect to x and then with respect to y at AB. You could take the partial derivative of f first with respect to y and then with respect to x at AB. Or you could take the partial derivative of f with respect to y and then the derivative of that again with respect to y at AB. So we have 4 different second partial derivatives. Now, if they're continuous, the order in which you take the partial derivatives doesn't matter. So the partial of f with respect to x, y at AB, and the partial of f with respect to y and x in the opposite order AB, they're always equal if these are continuous. So these are numbers, but these are the same numbers. And if you look at this as a 2x2 matrix, which is sometimes called the Hessian matrix, though the name doesn't matter, and you take the determinant of that. Now, if you have a 2x2 matrix, that is an array of 4 numbers written as like a square, the determinant by definition is AD minus BC. Right? So it's useful to memorize that definition, or you can just memorize what you get in this case. But this determinant is equal to the part, this times this. It's the partial of f with respect to x twice times the partial of f with respect to y twice minus this product, partial of f with respect to y at AB, times the partial of f with respect to x and then y and y and then x, but they're equal, so it's just this squared. So let's call this thing d at AB. So this is the analog of the second derivative, right? So what is the second derivative test? So first of all, it's a critical point. So the partial of f with respect to AB, partial of y with respect to AB are both 0. That's a necessary condition to start with. If this number, capital D, is positive, and partial of f with respect to x twice at AB is negative. Remember, in Calc 1, if the first derivative was 0 and the second derivative was negative, then you have a local maximum. And the same is true here. If this function capital D is positive and the second derivative is negative, then you have a local max at AB. If this quantity is positive and the partial derivative of x, f with respect to x twice, is positive, then you have a local minimum. Again, just as in Calc 1, if the first derivative is 0 and the second derivative is positive, you have a local minimum. If this number d of AB is negative, then you have a saddle point. If this number is 0, no information. The test is inconclusive. It's also inconclusive, of course, if this number D is positive. Well, if this is positive and this is not negative, this has to be positive. So they're either both positive or both negative. They can't be zero. None of them can be zero. All right, so let me spend some time working out local maxima and local minimum for functions. So examples. All right, so really the way to understand this is to follow the examples carefully. Suppose we have the function f of xy equals x squared plus 2y squared minus 4x plus 4y plus 6. And we want to find the critical points and then determine at those critical points whether we have a maximum or a minimum. So the partial of f with respect to x is 2x minus 4. And that's equal to 0 precisely when x is 2. Partial of f with respect to y is 4y plus 4, and that's equal to 0 precisely when y is equal to minus 1. So there's one critical point, 2 minus 1. All right. What about the second partials? So if I take the second derivative of f twice with respect to x, so if I differentiate this with respect to x, I get 2. If I differentiate first with respect to x and then with respect to y, I get 0. If I differentiate first with respect to y and then with respect to x, I get 0. And if I differentiate twice with respect to y, I get 4. So the determinant that I'm looking at is 2, 0, 0, 4. This determinant is 2 times 4 minus 0 times 0. That's 8, which is positive. So that's my number D. D equals 8 is positive. Partial of f with respect to x twice at the critical point 2 minus 1 is 2, which is positive. So therefore I have a local minimum at 2 minus 1. So you need to look at that for a few minutes and make sure you understand what's going on. Here we have a function of two variables, x squared plus 2y squared minus 4x plus 4y plus 6. So we want to find the critical points because those are the only places where you could have a local minimum or local maximum. And then distinguish, then decide what you have at that point, if it's possible. You want to use the second derivative test to find out, or we want to see whether the second derivative test will tell you if you have a local minimum or a local maximum or a saddle point, or if you get no information from the test. So the first derivative of this with respect to x is 2x minus 4. That's 0 when x is 2. derivative with respect to y is 4y plus 4. That's 0 and y is minus 1. These are the only values where both first derivatives vanish. So there's one critical point. 2 comma minus 1. Then you look at the second derivatives. Differentiate this with respect to x, you get 2. Differentiate with respect to y, you get 0. Differentiate this with respect to y, you get 4. This with respect to x, you get 0. So you get 2, 4, 0, 0. That determinant, which is the number d, is 8. So this is positive. But the first derivative, the second derivative of f with respect to x twice, at any point is positive is 2. So if this is positive and this is positive, that means a local minimum. That's the story. Now, sometimes we also look for the absolute maximum or absolute minimum on a region R. And again, this is exactly analogous to what you did in Calc 1. You might have a function that looks like this. And let's say this is the xy axis. Yeah, that's the x-axis. And this is x equal a. And this is x equal b. And this is the curve in this region. So on this curve, you have local minimums here and here. You have local maximums here and here. But you want to find the absolute maximum, and that is the point where the curve is as large as possible. So in addition to looking at the endpoints inside the interval, you have to look at the values inside the interval. You also have to look at the values of the function on the boundaries of the interval. And if you look at these, this point, this is a local max, and this is a local max. But this one right here, is the only absolute max. You have a local minimum here and here, but this point is the absolute minimum. So there's the analogous notion in functions of two variables. You want to find the absolute maximum or absolute minimum of a function in a region. And so you have to examine the values of the function f of x, y at critical points and on the boundary of the region. So let's try and do an example or two of this. Suppose I take the function f of xy equal to xy minus 8x minus y squared plus 12y plus 160. And I want to consider the triangular shape region R, which is going to be all points x, y in the plane, where x is between 0 and 15, and y is between 0 and 15 minus x. So that region looks like this. If this is 0 and 15, x is between 0 and 15, and y is between 0 and 15 minus x, which means we're looking at this region R, this red triangle. So we have to find the values, the critical points of the function in this region, and also examine it on the boundary, right? So let's look for critical points. So the partial of f with respect to x is y minus 8, y minus 8, that's all it is. And that's equal to 0 when y is equal to 8. Partial of f with respect to y is x minus 2y plus 12. And when is that equal to 0? Well, that's equal to 0 when 2y is equal to x plus 12. Or sorry, let's make it when x is equal to 2y minus 12. But if y is equal to 8, then x is equal to 2 times 8 minus 12. 16 minus 12 is 4. So the only critical point is at the point 4, 8. Now, okay, so that's one critical point, 4, 8, somewhere up around there. But we also have to look, and what is the value of the function at 4, 8? F at 4, 8 is xy 32 minus 8x 32 minus y squared 64 plus 12 times y 96 plus 160. So that's 160 plus 32 is 192, if I did my arithmetic correctly. So at this critical point, the value of the function is 192. But to find the absolute maximum or minimum, we know, in addition to the critical point, we have to look at the function on the boundary. So the boundary consists of 3 lines. So you have this line, y equals 0, and x between 0 and 15. So f of x comma 0, when y is 0, my function is minus 8x plus 160. And this has its maximum value when x is 0. You get 160. And its minimum value when x is 15. 8 times 15 is 120. So 160 minus 120 is 40. So on this line, the function goes from 40 to 160. Right? That's this line. So this is one line. The second line is when x is 0 and y goes from 0 to 15. When x is 0, my function f of 0y is minus y squared plus 12y plus 160. And what is this? So I want to find the maximum and the minimum value of this function for y between 0 and 15. If I differentiate this with respect to y, so the partial of f with respect to y at 0y is minus 2y plus 6. That's equal to 0 at y equal 3. So at y equal 3, and the second derivative is minus 2, so that's going to be a local maximum. So f of 0, 3 is minus 9 plus 36 plus 160. So this is 27. So this is 187, I think. Oh, sorry. Let me do this function. I'm trying to squeeze it into a little space, but let me just do it a little more carefully here. So partial of f with respect to y, sorry, on this line, x equals 0. When x is equal to 0, the function is minus y squared plus 12y plus 160. So the derivative is minus 2y plus 12, or y equals 6. And so for this f at 0, 6 is equal to minus 6 squared plus 12 times 6, 72, plus 160, minus 36 plus 72 is 36, 160. This is 196. So f of 0, 6 is 196. At the endpoints of this line, f of 0, 0 is 160, and f of 0, 15 is minus 15 squared, 225, plus 12 times 15, which is 180, plus 160. So this is 340 minus 225, which I think is 115. So on this line, the function goes from 115 to 196. On this line, the function goes from 40 to 160. And what about on this line? So this is the line y equals 15 minus x. So I have to calculate f at x comma 15 minus x. And so if you substitute this into my function, this is xy, x times 15 minus x, minus 8x minus y squared, 15 minus x squared, plus 12 times y, which is 15 minus x, plus 160. And the book does this calculation, so why not just see what it says it gets? When you plug this in, you get the function minus 2x squared plus 25x plus 115. So again, for this function, for x between 0 and 15, you have to find the value at the endpoints. I mean, this is a parabola that's going down. You have to find the value at the endpoints and at the maximum. So you have three, so you can find the largest value on the boundary, right? You get the largest value on the boundary. You compare it to the value in the middle. Whichever is the largest value is the absolute maximum. Whatever is the smallest value is the smallest maximum, is the absolute minimum. Okay. All right, well, okay. So what did we do today? We reviewed the tangent plane and the linear approximation to a function using the tangent plane. And then we did one new thing, which was the second derivative test for functions of two variables. So this is the analog of the second derivative test for a function of one variable. In this case, you want to find the absolute, you want to find the relative maxima and minima of a function. This will happen at the critical points. And at those critical points, you can use the second derivative test to find whether you have a local minimum, a local maximum, a saddle point, or no information. And when you have a region in the plane, a closed bounded region, and you want to find the absolute maximum minimum of the function in that region, you have to evaluate the function at the critical points, but also on the boundary, because the absolute maximum will take place either in the interior of the region at a critical point or on the boundary. So that is usually a bit of work to do, but it's always comforting to be able to do the work and see you got the right answer. And I'm always going to give you odd-numbered problems so you can check your work in the back of the book. And I'm available this week, Monday, Tuesday, Thursday on Zoom at 7 o'clock to answer questions. And if none of those times work, then just send me an email. We'll figure out another time. All right. So what we just done is we've concluded what we're going to cover in the chapter on functions of several variables. The next topic, which will start on Wednesday, is multiple integration in chapter 16. And we're only going to do integration with rectangular coordinates. We're not going to do integration with polar coordinates or cylindrical coordinates or spherical coordinates. So we're really just going to cover section 16.1 and 16.2. And then we get to what is really the high point of a course in vector calculus, which is chapter 17, which has the perhaps unsurprising title of vector calculus. And we'll be studying that for the duration of the semester, which doesn't really have that much longer to go. But okay, that's where we are. So we're covering a lot of material, which is difficult material. And I can only urge you to come to a problem session and ask some questions. Even if you don't have any questions, come to a problem session and I'll invent a question that you could ask. But you should really, you really don't learn anything, or you don't learn as much as you might if you don't work the problems and ask questions about the ones that you find mysterious in some way. That's the whole point of it all. Okay. All right. Anything else before we quit for the morning? If not, then enjoy the rest of the day. And I will see you Wednesday morning at 11 o'clock.
Have a good one.
Thank you. I will put the announcement on Blackboard about changing the exam date. Okay. All right. Bye all.